Good morning to one and all. Is the screen visible? Okay. Good morning to all. We'll start today's class on the cyclic codes. Okay. So from where we had left in the yesterday's class or in the last class, we are going to start from there. So in the last class we had seen a definition of cyclic codes. We had seen a problem on how to solve the cyclic codes. So the continuation of that we are going to see here. So the cyclic codes can be given in two different formats. One is a systematic form of generating the matrix. Second one, non-systematic form of generating the matrix. So systematic form is known to everyone. As you had seen in linear block codes, x is equal to m is to c. Message codes followed by check bits. Message bits followed by check bits. M is your message bit, C is your check bits. So totally we get the code vectors X. So in cyclic codes, we'll be seeing both the topics of systematic form of generating and non-systematic form of generating. So first, let us see the non-systematic form of generating. Yeah. Before starting the non-systematic form of generating, we'll see that whether we had completed this topic. No, we had seen till this topic only. Yeah. In the last class, we had solved this problem. A generator polynomial of n comma k, 7 comma 4 cyclic codes with generator polynomial pq plus p plus 1, and we had found the code vectors for all the different combinations of messages. So I think this table everyone would have verified and checked it. Code vectors of 7 comma 4 cyclic codes for the generating polynomial pq plus p plus 1. We had obtained non-systematic code vectors. Next, we had seen that a property that it satisfies is when we do a cyclic shift of either left side for any bit, it will also produce another code vector. So then the cyclic property is being verified. I think most of you would have done the verification for the remaining code vectors also. So far what we had seen was the non-systematic form of generating. An example of that. So now let us see the systematic cyclic codes. How do we generate systematic cyclic codes for the entire blocks? For example, let us consider there are k message bits and q check bits or n minus k check bits as in equation 3.4.11. So x is the code vector, k is the message bits, and n minus k is the check bits. So I can write in the form that m of k minus 1, m of k minus 2, m of k minus 3 till m1 m naught is to c of q minus 1, c of q minus 2 till c1 c naught, as in equation 3.4.12. So here the check bits form a polynomial. The check bits c form a polynomial series. So I can write the check bits as c of p is equal to cq minus 1 p power q minus 1 plus cq minus 2 p power q minus 2 plus cq minus 3 p power q minus 3 till c1 of p plus c naught, as in equation 3.4.13. So how do I get this? Is that by multiplying it with the p submatrix. So p submatrix of the check bit q minus 1, then next p submatrix of q power minus 2, next is the check bit matrix of c p power minus 3, and so on till p c1 of q and c naught. So in general we can write the check bit polynomial can be obtained by the formula remainder of p power q into m of p divided by g of p. C of p is equal to remainder of p power q m of p divided by g of p. So where p power q is the message polynomial, p power q is the message polynomial, pq into m of p is the generator polynomial. Message polynomial is different, generator polynomial is different, and c of p is the check bit polynomial. So what do we do is that p of p should be multiplied. So here multiply message polynomial by p of p, whatever message we get, message in the sense mk1 mk minus 1 mk minus 2 mk minus 3 till m1 m naught. So multiply that with p power q, then divide that p power q into m of p by generator polynomial g of p. So g of p will be given in the problem, m of p will be given in the problem, and the remainder of the division, whatever remainder we get, so that is your check bits polynomial c of p. So let us see that with an examples also. So keep in mind generation of code vectors in systemic form. The formula is c of p is equal to remainder of p power q m of p divided by g of p. First we should multiply the message with p power q, then divide that with generator polynomial g of p, then the remainder what we get is c of p. So the generator polynomial, the question is given for a generator polynomial. The generator polynomial of a 7, 4 cyclic code is g of p, p power q plus p plus 1. Find all the code vectors for the systemic codes. In the previous problem we had seen non-systematic. Here we are going to see systematic. So here from the given question we can find n value, which is 7, k value, which is 4, and from that we can obtain q, which is n minus k is equal to 3. So Since there are 4 message bits, we'll get 16 message vectors. We'll get 16 message vectors. So take the 16 message vectors, right from 4 zeros to 4 ones, as we have done in the previous table. So in that, I consider 0101. Let us assume that 0101 is the message vector or the message polynomial. Okay. Now, what we are going to do is, first we'll be finding the message polynomial for the message 0101. So how do we find this? As we had seen in the non-systematic, m3 into 0, m2 into 1, m1 into 0, m0 into 1 in the place of degrees. So this degree is p p0, this degree is p power 1, this degree is p power 2, this degree is p power 3. So we get, when you substitute this, we get the polynomials as p square plus 1 as in equation 3.4.15. Now we had got the m of p. M of p is obtained. So from equation 3.4.14, m of p is obtained. So we need to find, we should see where is g of p and where is p of q. Next, after determining m of p, we need to find g of p. So g of p is already given in the question, I think. So in the question it's given p cube plus p plus 1. So write as it is. So remaining term what we have to find is p power q. So p power q can be obtained easily. Why? Because q is known. So q is obtained from n minus k. N is 7, k is 4. So we get q is equal to 3. So p power 3. So multiply that with the message polynomial. So p power 3. So our message is, we have taken example 0101. So for that our message we had obtained p square plus 1. So p cube into p square plus 1. So simply do manipulation. P cube into p square, we get p power 5, and p cube into 1 is p cube. So here there is a typo error. It is not q cube, it is p power 3. There is a change in this, it is p power 3. So now we can split that in the equation and write in terms of individual bit sequences. In terms of p power 0, p power 1, p power 2, p power 3, p power 4, p power 5. Since we are having only values for p power 5 and p power 3, the remaining all polynomials of the individual bit sequences will be 0. So 1 into p power 5, in p power 4 it is 0, then in p power 3 it is 1, so p cube plus 0 p power p square plus 0 p power 1 plus p power 0 into 0. So I can write the p cube of m of p as this equation: p power 5, 0 p power 4 plus p cube plus 0 p square plus 0 p power 1 plus 0 p power 0. So this is how do we get p cube into m of p. So next, g of p is given. So expand this g of p also, such that our division would be much easier. Why we are doing this is that in order to simplify the division procedure in terms of polynomials. Okay. So p power 3 we have, so p power 3 0, we don't have p square, so 0 p square plus p is there plus 1 is there, so write as it is. So any doubts in this determining p cube into m of p? Let me see in the chat box. Any questions or doubts you can put in the chat box. Determining p cube into m of p and finding g of p. G of p would be given in the question obviously. And how do we split it and write? If no queries, shall I proceed? Okay. Next is to perform the division p power q m of p divided by g of p. So use our division principle, write p power q m of p inside p power 5 plus 0 p power 4 plus p cube plus 0 p square plus 0 p plus 0. So write as it is. Now our g of p is p cube plus 0 p square plus p plus 1. So write it here. P cube plus 0 p square plus p plus 1. So now we need to do division appropriately. So in what if we multiply with p cube, we'll get p power 5. We should see that. And since we all are familiar with basic mathematics, so p cube into p square will give p power 5. So write in the quotient p square or p power 2. So multiply that p square into p cube. So we get first term as p power 5, multiply with the second, we get p power 4, multiply with the third, we get p cube, multiply with the next, which is 1, we get p square. So multiply and write it, we get p cube into p square is p power 5. So next is 0 p power 4, next is p cube plus p square. So then the important procedure that we are going to do is, rather than subtraction, we are going to do only modulo 2 addition. Keep in remembrance, in information theory and coding, most of the things that we do is modulo 2 addition only. So when we do modulo 2 addition, what will happen? So here 1 1 1 1 is 0. So here 0 0 is 0. Here 1 1, it is 0. Here it is 0 1. So 1. Here the remainder will be 0p as it is and 0 as it is. So again, if you do, if you want, you can multiply it with, you need to do multiply with something to bring it p square. It's not possible. We cannot introduce p power minus 1. We cannot introduce at all. So the remainder will be always p square plus 0p plus 0. Why? Because the degree of polynomial of p0 is less than the degree of the divisor, its degree is lesser, so we cannot further do division. So keep in remembrance. The remainder polynomial is having the highest degree, p square, whereas the divisor has greater than the degree of that. So we cannot do further division. Okay. So thus the remainder of the polynomial will be p square plus 0p or 0. Both will represent equal to p square. So in the division of p cube m of p by g of p. So therefore the remainder of this will be p square plus 0p plus 0. Remainder of this will be p square plus 0p plus 0 or simply p square. So this represents your check bits polynomial for the message vector 0101. So we get q is equal to, if q is equal to 3, with message vector 0101, the 0101 is the message vector. For that, the check bits polynomial will be p square plus 0p plus 0. So thus when we interrupt this in the form of bits, we can write c of p is equal to c2p square plus c1p plus c naught, as in equation 3.4.13. So when we expand that, the check bits will be p square plus 0p plus 0. Or we can write in the place of c2 it is 1, in the place of c1 it is 0, in the place of c0 it is 0. So this is how to find the check bits for a systematic cyclic code. So systematic cyclic code will have the check bit c2 c1 c0 as 1 0 0 for the message vector 0101. You can see always the systematic form is written in terms of x is equal to m is to c. Okay, mk minus 1, mk minus 2 till m naught, and check bits is written cq minus 1, cq minus 2 till c1 c naught. So here we are going to substitute for this example. Message bits are 4, so m3 m2 m1 m naught, c2 c1 c naught. So our message bit is, let me see the message bit, m3 m2 m1 m naught. What we had seen, we had taken an example. Our message vector is 0101. So for 0101 we got 100 as the check bits. So the combination of these two will give the code vector for this particular sequence. So 01. So the message bits is 0101 which we have taken, and code and sorry, on the check bit we got is 100. So combine these two. So 0101 100. See serial number 6. Serial number 6 for the message bit 0101. It is 0101, which is the message, and code vector is 100. So this is how to find the code vectors for a systematic format. So any doubts in this problem? Any doubts? Now, I request everyone to take a screenshot of this slides, all the three slides. Work out for the remaining message bits as we had done in the previous class. Why? Because only this will give you an idea how the systematic code is being generated, how the non-systematic codes are being generated in cyclic codes. Take screenshot of this. Take screenshot of this slide. I'll give you 2 or 3 minutes time. Take screenshot of this slide. Then the remaining 2 slides also you take screenshot and check for the remaining messages. Let me check in chat box for any queries. Yeah, what is the purpose of modulo 2 addition in information theory and coding? So when we do division, for example, when we do division, we need to cancel two equations. We'll be writing so what you call x power 5 plus x square plus 1 as a quadratic equation, and we have another quadratic equation x cube plus x square, for example x square, yeah, let it be x square, x cube plus x square. So when you divide, how will you divide? You'll be dividing it by x power 5 plus x square plus 1 divided by x cube plus x square. So for cancellation, what do you do in division? You use subtraction. In the same way, when we do information theory, in information theory and coding, for a specific application of subtraction, we should not use the mathematical subtraction at all. We need to use modulo 2 addition operation. So modulo 2 addition operation is your XOR gate operation. Since we deal with binary zeros and ones for the time being, because our machines which were what do you call which were operating, all the machines are operating in binary zeros and ones. So the manipulation of that should be done in zeros and ones only. So when we do 0 plus 0, we get 0. When we do 1 plus 0 or 0 plus 1, we get 1. And when we do 1 plus 1, we get 0. The meaning is, for XOR gate operation, when the inputs are same, the output will be 0. When inputs are different, we get outputs as 1. So this has made an attraction in solving many of the problems. For example, in this division itself, in the division itself, these two are similar. P power 5 and P power 5. Let me slide show. P power 5 and P power 5 are similar. So same inputs. If same inputs are there, the conclusion is that there is no error. For example, if x is P power 5 and y is P power 5, will you get an error? No, obviously we will not get an error. If x is different and y is different, for example, x is 1 and y is also 1. So when you do modulo 2 addition, what we will get? We'll get output as 0. So we don't get any errors. So the main purpose of using the modulo 2 addition is that if I have x as some bits of sequences and y with the same bits of sequences, if you do modulo 2 addition, and if it results in 1, it resembles that there is an error. There is an error. And if you get only zeros, it resembles that there are no errors. So now can you tell me in what way this model to addition is used in information theory? First, it is used in error detection. I'll write an example. X is equal to 1 0 1, y is equal to 1 0 0. For example, I give an example for you. X is equal to 101, y is equal to 100. Do x modulo 2 addition. On doing x modulo 2 addition y, we get, yeah, as you said, 0 1 1. So in which bit the error is present? If you get everything as 0, it resembles no errors. So I get a error. We should not say last bit. Error in third bit. Error in third bit. Error in the third bit. So error in the third bit resembles that this x and y. X when it is transmitted has no errors, but in y we have an error. So this is used in error detection first. Then correction is another criteria. Okay, understood now? Why do we use modulo 2 addition?
Sir, okay, sir. I'm asking that right?
No, I'm getting a break in your voice. So kindly type in chat box. No issues. For detection of the received signals and correcting those bits, whatever bit might be, is the error, is the main purpose of using modulo 2 addition. So error in third bit is identified by doing modulo 2 addition. By doing modulo 2 addition. You take any other operation also. Yes, modulo 2 addition is the only way. You take inverter gate, NOT gate. For NOT gate, we require at least 2 inputs. So NOT gate is out. Do AND gate. You check and do for X and Y AND gate and tell me. See, take the same X and Y. From seeing itself, X and Y, I can tell you that third bit is the error. Now you use the logic of AND gate or OR gate or NOR gate or NAND gate. Use any other gate and tell me. You check, it's a random value only, no. Kindly check, you won't get. AND gate is 100, but X and Y, see the X and Y. First bit is not an error. Our X and Y, X is 101, Y is 100. First bit is not an error. So AND gate is eliminated. Yes. Then do for OR gate. OR gate. OR gate 101. The last bit that it had found is correct, but it is showing first bit is also an error. But X is 101, Y is 100. First bit is not an error. So OR gate is out. OR gate is out. Then take what another gate is NOR gate. No, no, perform with NOR and see. Perform with NOR and see what you get. You will understand only when you solve this. Though I give information, only when you do a small exercise on this, you will get more knowledge on why we use modulo to addition. Why? Because the modulo to addition principle is when inputs are different, output will be high. When inputs are same, the outputs will be low. So with that principle, the inputs to that exclusive OR gate or to the modulo to addition, if you give different inputs, it will be high. If you give same inputs, it will be low, meaning that X and Y are the inputs. X is your transmitted signal, Y is the received signal. Now kindly check for NOR and AND also. Okay, you said you had understood, so okay, right? You can try also. So then I'll show the next slide. Take screenshot of that. Kindly take screenshot of this. Because this procedure you're going to do for the remaining message bits. So kindly make a screenshot. Because afterwards when you take some after 1 week or 10 days or so, you will not be able to understand. Metal is shared. If you take and see, you will not be able to understand how you had done this. So I'm giving you sufficient time. So take a screenshot of this, because there is a lot of difference between systematic and non-systematic codes of generation. So if you are familiar with the systematic codes of generation and non-systematic codes of generation, whatever might be the problem being given, if they ask you to do non-systematic, you can perform it. If they ask you to do systematic, you can perform it. It will be easier. I'll give you 2 or 3 minutes time for taking screenshot. I'll move on to the next slide. Take screenshot of this. Because for all these different combinations, you need to solve and check whether you're getting this. Then I'll tell you how to compare systematic and non-systematic codes. So there in non-systematic codes, we don't know where is C is present. Check bits are present in the messages. it will be jumbled. But whereas in systematic, we can easily identify that the last sequence of bits, depending upon the question, where check bits are present. So after taking the screenshot of this slide, also try for each and every sequences. Already I had done it for serial number 6. I had done it for serial number 6. Check for the remaining message bits also. And if you have any doubts, put in the chat box. We'll discuss in the chat box. Kindly take the screenshot of this slide. Take a screenshot of this slide and try for the different message bits. Remaining message bits. I done it for serial number 6. You try for the remaining. And for any queries or questions, you can type in the chat box. I will check the queries and I'll answer you. Yeah, as you said, in NOR gate 110. So the first bit is also an error, second bit is also an error. And in some other gate that you're saying 010. So first bit is not an error, okay. But second bit it is an error. It is showing like that. So X is 101, Y is 100. See, first bit no error. Okay, very good. But the second bit it is showing. It is not supposed to be an error, but it is showing as an error. So when we do X modulo 2 addition of Y, we can find, we will get the value as 001. Value is value will is 001. So hence this has detected it correctly. This has detected it correctly. That third bit is the error bit. So you would have been wondering when you studied digital electronics or digital principal system design, what is the use of all these gates? Is that this XOR gate is an error detection gate also. This is also an example, or this is also an application in addition to the remaining. Okay. Kindly do the systematic code analysis for the remaining codes, remaining messages, and after solving it in a paper, For each and every message bit, solve it in a paper, and after completing for all the messages, just write your register number, your name, scan it and put it in our class WhatsApp group. Some 10 minutes is enough, I think so. So 10, yeah. Take 10 minutes of time, solve it and send it. So meanwhile, if there are any queries, you can type in the chat box. I hope you would have taken screenshot of this slide. I'll check for any queries in the chat box. I'll try to address the queries. Sai Shrikar, you didn't took screenshot of the slides, sir. Yeah. In that, have you taken the last slide screenshot? Third slide. A table. If not, tell me. I'll show it again. Okay, right. So in the table, I had solved for only serial number 6. Message vector is, sorry, message bit is 0101. Now for the remaining combinations, right from serial number 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. For those serial numbers, you find as how you're getting this corresponding X. So that is the question. Understood now? As we had done in the previous class problem. In the previous class, I had assigned you a message bits. So now I'm not assigning any message bits to you. Instead of that, I'm saying you to solve for the remaining bits except serial number 6. So that procedure you do in a paper, solve it. Time, I'll give you enough time. If you say okay to proceed for the next problem, I will proceed. Till the time is there, you solve it in a paper. After completing the procedure, for example, message 1, 4 zeros. I had done PQ of M of P power Q is P power 3. Then find PQ M of P. Then divide that with G of P. So that procedure. Then you will get a message. Sorry, then you will get a reminder. So that reminder is your C2, C1, C0. Similarly, for the next message, 0001. For that you do. Next 0010. Same procedure you do and check whether you're getting the table correctly. I had solved for serial number 6. I'm saying it, trying to say that you solve it and see such that you'll get practice on this systematic codes, systematic cyclic codes. Okay. I'll put the table again. For any doubts, you can put in the chat box. I hope everyone would have completed. If yes, kindly put in the chat box such that we can proceed for the next type of problem or the next topic. I'm waiting for your information only. Okay, I'll wait. Okay, carry on, carry on. If you haven't completed, carry on. I'll wait. Then we'll go for next topic. Okay, for message bit 0011. So we'll do it. And we'll see. I'll do it in Jamboard. We'll see. 001.
Morning, sir. I got I mistake.
Yes, yes.
I got the answer, sir. I have done a mistake.
Okay, you got the correct answer or some variations?
A correct answer only, sir. Again, I checked it.
Okay, okay. But check bits. We'll see. No problem. I'll solve it also. No issues. Uh, I'm doing for bit message 0011 in Jamboard. So I will mute my mic and I'll do it. So kindly try to follow how it is being done. Okay. So I'm muting my mic and I'm solving it. Okay. You can follow these steps in procedure. Yeah, I hope you would have got this for 0011. P cube m of ps p power 4 plus p.
Sir, sir, sir,
Yeah, here I wrote it wrongly.
Power
GP,
4 plus
G of P
P
should
cube,
be
sir.
in this place. Yeah, yeah, yeah. I wrote it wrongly, so I'm interchanging. So wait a minute. They
Sir,
should come here. Okay.
sir.
Yes, yes. I'm doing that.
P power Q M of P you did wrong, sir.
Yes, yes, yes. So just now I had found it. So I'm correcting it.
Sir, P power Q M of P power 4 plus P cube, sir.
I think now you would have got the answer, correct answer, right? So I had chosen 00. Just a minute. I had chosen the message bit as 0011. For that, I got C2, C1, C0 as 101 in the table. Now let us see what I had got in the Jamboard. You can see from the Jamboard, I had got for the message bit, which I had chosen, message bit I had chosen 0011. So I had done finding m of p, which is p power 1 plus 1 from the question g of p, p cube plus p power 1 plus 1. Q is 3 from the for this problem, so p power q is p power 3. So multiplied with the message polynomial m of p, so I got p power 4 plus p power 3. So that divided by generator polynomial. So p cube plus p power 1 plus 1. So I wrote it with all the coefficients for better simplification. Then I had done modulo 2 addition and found out the remainder. So this is your remainder. So remainder is 1 p square plus 0 p1 plus 1. So the equivalent bits are, check bits are c0, c1, c2. We get 101. So let me see in the table. The table for 0011, 101 is the check bits. So this is how to find the systematic code vectors. I think those who had doubts, you would have got clarified how to solve. Ah yes, Lakshman, you can't open Jamboard. When I visualize, you need to see. So there is still that settings has not been opened for you. Since instantaneously I opened the Jamboard, it is not letting you inside. Inside what you want to submit images? Yeah, just to share it in our WhatsApp group. You're having WhatsApp group now. In that you can share the solved answers. So I think time is running for a small problem. Okay. Kindly await. I'll share you the attendance sheet. Kindly see in the chat box, attendance sheet is circulated. So those who fill this attendance sheet or those who fill this Google form, attendance will be marked only for them. In the next class, we will start how to form a generator matrix, both systematic and non-systematic. In these two classes, we have seen how to generate code vectors for systematic codes and non-systematic codes. A problem based on that we had solved it. Now in the next class, we'll be solving how to generate a generator matrix. So in the tomorrow's class for both systematic and non-systematic. Because in these questions, G of P is given. In the next section, we'll be dealing as how to obtain this G of P if code vectors are given or if polynomials are given. Okay, we'll see that in next class. So kindly fill this attendance form, and after filling, you can leave. For any other doubts, I'll be staying in the meeting. You can ask in chat box.